By starting with the name of Allah, Bismillahir Rahmanir Rahim. Assalamu alaikum. I am Sharmeen Noor from the Department of VS Biotechnology. This presentation is submitted to Dr. Hammad. The topic of my presentation is Explain AUFBAU's role and electronic configuration. So, as electronic configuration, first of all, we need to know what is quantum mechanics. Quantum mechanics is a fundamental theory in physics that provides a description of the physics property of nature at the scale of atoms and subatomic particles. It is the foundation of all the quantum physics, including quantum history, quantum field theory, quantum technology, and quantum information science. Better than any previous model, quantum mechanics does explain how the atom behaves. Quantum mechanics treats electrons not as particles but more as waves, light waves, which can gain or lose energy. But they can't gain or lose energy just any amount of energy. They gain or lose a quantum of energy. Quantum mechanics arose gradually from the theories to explain observations which could not be reclined with the physical classics, such as Max Planck's solution in 1900 to the black-body radiation problem and the correspondence between energy and frequency in Albert Einstein's in 1905 paper, which explained the photoelectric effect. These early attempts to understand microscopic phenomena, now known as the old quantum theory, led to the full development of quantum mechanics in the mid-1920s. Quantum mechanics allows the calculation of probabilities for how physical systems can behave. It is typically applied to the microscopic systems, molecules, atoms, and subatomic particles. Predictions of quantum mechanics have been verified experimentally to an extremely high degree of accuracy. A basic mathematical feature of quantum mechanics is that probability is found by taking the square of the absolute value of a complex number. This is known as the Born rule. For example, a quantum particle like an electron can be described by a wave function which associates to each point in space probability amplitude. So coming toward the next, atomic orbitals. What is atomic orbitals? In atomic theory and quantum mechanics, an atomic orbital is a mathematical function describing the location and wave-like behavior of an electron in an atom. This function can be used to calculate the probability of finding an electron of an atom in any specific region around the atom's nucleus. The term atomic orbital may also refer to the physical region or space where the electron can be calculated to be present as predicted by the particle mathematical form of the orbital. Much like the Bohr model, the energy level in the quantum mechanics describe locations where you are likely to find an electron. Remember that orbitals are geometric shapes around the nucleus where electrons are found. Quantum mechanics calculates the probabilities where you are likely to find electrons. Each orbital in an atom is characterized by a unique set of values of the three quantum numbers n, l, and m, which respectively correspond to the electron's energy, angular momentum, and an angular momentum vector component, the magnetic quantum number. Each such as orbital can be occupied by a maximum of two electrons, each with its own projection of spin. The simple names s orbital, p orbital, d orbital, and f orbital refer to the orbitals with angular momentum quantum number L, which is equals to 0, 1, 2, and 3 respectively. These names together with the value of n are used to describe the electron configuration of atoms. They are derived from the description by early spectroscopy of certain series of alkali metals spectroscopic lines as sharp, principal, diffuse, and fundamentals. Orbital for L, which is greater than 3, continue alphabetically. So, coming toward the next, atomic orbitals. What is atomic orbitals? Of course, you could find an electron anywhere if you looked hard enough. So scientists agreed to limit these calculations to locations where there was at least a 90% chance of finding an electron. Think of orbitals as sort of border for spaces around the nucleus inside which electrons can ever be in one orbital. The orbital just defines an area where you can find an electron. What is the chance of finding electron in the nucleus? Yes, of course, it's 0. There are not any electrons in the nucleus. What is atomic orbital? So, Each shell occupied by a maximum of 2 electrons, each with its own projection. The simple names are s orbital, p orbital, d orbital, and f orbital. The atomic orbital is a mathematical function describing the location and wave-like behavior of an electron. So coming toward the next, as energy levels. Quantum mechanics has a principal quantum number. It is represented by a little n. It represents the energy level similar to Bohr's model. N is equals to 1 describes the first energy level, n is equals to 2 describes the second energy level, n is equals to 2, and so on. Each energy level represents a period or row on the periodic table. It's amazing how all this stuff just fits together. As the boxes show, the red is n is equals to 1, orange n is equals to 2, yellow n is equals to 3, green n is equals to 4, blue n is equals to 5, indigo boxes are n is equals to 6, violet n is equals to 7. So what is energy levels? A quantum mechanics system or particle that is bound, that is confined, spatially can only take on certain discrete values of energy called energy levels. This contrasts with the classical particles which can have any amount of energy. The term is commonly used for the energy levels of the electrons in atoms, ions, or molecules which are bound by the electric field of the nucleus, but can also refer to energy levels of nuclei or vibrational or rotational energy levels in molecule. The energy spectrum of a system with such discrete energy levels is said to be quantized. There are 2 energy levels for electron. The first one is excited state and the second one is ground state. So, the energy levels for an electron in an atom: ground state and excited states. After absorbing energy, an electron may jump from the ground state to a higher energy excited state. In chemistry and atomic physics, the electron shell or principal energy level may be thought of as the orbit of one or more electrons around the atom's nucleus. The closest shell to the nucleus is called the one shell, also called K shell, followed by the second shell or L shell, then the third shell, which is M shell, and so on further and further from the nucleus. The shells correspond with the principal quantum numbers. N is equals to 1, 2, 3, 4, and so on are labeled alphabetically with letters used in the X-ray notation K, L, M, N. Each shell can contain only a fixed number of electrons. The first shell can hold up 2 electrons, the second shell can hold up to 8, 2 plus 6 electrons. The third shell can hold up to 18, 2 plus 6 plus 10, and so on. The general formula is that the nth shell can in principle hold up to 2 and 2 electrons, since the electrons are electrically attracted to the nucleus. So coming toward the next sub-level, specific atomic orbitals. Electrons exist around the nucleus of an atom in discrete specific orbits. Electrons cannot just exist at any distance from the nucleus. These orbits are called levels, and we number 1, 2, 3, 4, and so forth, with the first level being the orbit closest to the nucleus. The levels can be broken down into sublevels. We have S, P, D, and F sublevels. Level 1 has sublevel and S. Level 2 has 2 sublevels, S and P. Level 3 has sublevels S, P, and D. Level 4 has 4 sublevels S, P, D, and F. These are pictures. Each energy level has one or more sublevels which describe the specific atomic orbitals for that level. N is equals to 1 has one sublevel, the S orbital. N is equals to 2 has 2 sublevels, S and P. N is equals to 3 has 3 sublevels, S, P, and D. N is equals to 4 has 4 sublevels, S, P, D, and F. These are 4 types of atomic orbitals, S, P, D, and F. Each of these sublevels represent the blocks on the periodic table. The blue R is equals to S block, yellow is equals to P block, red is D block, green is F block. Coming toward the next, orbitals. The sublevels contain orbitals. Orbitals are spaces that have a high probability of containing an electron. In other words, the orbitals in an area where the electrons live. There can be 2 electrons in one orbital. The maximum, the S sublevel, has just one orbital, so can contain 2 electrons max. The P level has 3 orbitals, so can contain 6 electrons max. The d sublevel has 5 orbitals, so can contain 10 electrons max, and the 4th sublevel has 7 maximum. In the periodic, orbitals are represented by the boxes. So, some things to notice. Level 1 does not have a p or d or f sublevel, only a sublevel, so there is such long as 1p. In the s block, electrons are going into s orbitals. In the p block, the s orbitals are full, new electrons are going into the p orbitals. In the d block, the s and p orbitals are full, new electrons are going into the d orbitals. What about the f blocks? So coming toward the next, the objective C. In the energy level n is equals to 1, the sublevel is F. The total orbitals are 1, which is first orbital, total electrons 2, total electrons per level 2. In energy level n is equals to 2, the sublevel is S and P, and in S1 total orbitals 2s orbital, in P 3 total orbitals 2 p orbitals. The total electrons in 2 orbital are 2 and the 2 p orbitals are 6. The total electrons per level is equals to 8. The so on, n is equals to 3 and n is equals to 4. So what are these orbitals? So the level 1 does not have a p or d or f sublevel, only as in s level. So there is no such thing 1p or 1d or 1f. To distinguish between different s levels, we call them 1s, 2s, 3s and 4s. The p sublevels are called 2p, 3p and 4p. There is no d sublevel until the third level. The d sublevels are called 3d and 4d. The only f sublevel we study is the 4f. When we fill electrons into an atom, we start with the first level because it is closer to the nucleus and thus lower in energy. Then we will fill in the second level and so forth in general. So by putting electrons into orbitals as in the periodic table of the elements, let's pretend we are moving students into campus housing. This housing is on 1st, 2nd, 3rd and 4th street. The levels, which are levels. There are houses on these streets. The houses are called S, P, D and F houses. The S house has 1 bedroom. The P house has 3 bedrooms and the D house has 5 bedrooms, and the F house has 7 bedrooms. In each bedroom there is a bunk bed. So the 2 students can sleep in a bedroom. Answer these questions. The first one, how many houses on 4th street? Obviously 4. How many students can live on 3rd street? In 3rd street there are 18 students. How many bedrooms on 2nd street? There are 4 bedrooms. How many students can live in a P house? So 6 students can live. How many bedrooms in a P house? Only 3 bedrooms. So how many bedrooms in a F house? 7 bedrooms. How many students can live in a F house? So 14 students can live in F house. How many students can live on 1st street? Only 2 students can live on 1st street. How many students can live on 2nd street? 8. In this analogy, streets are levels, houses are sublevels, bedrooms are orbitals and students are electrons. So as coming towards the next, what is electronic configuration? The main topic is, what do I mean by electron configuration? The electron configuration is the specific way in which the atomic orbitals are filled. Think of it as things similar to your address. The electron configuration tells me where all the elements live. So in atomic physics and quantum chemistry, the electronic configuration is the distribution of electrons of an atom or molecule or other physical nature structured in atomic or molecular orbitals. For example, the electron configuration of the neon atom is 1s, 2s, 2p6 using the notation. So electron configuration describes each electron as moving independently in an orbit in an average field discredited by all other orbitals. Mathematically, configurations are described by slated determinants. or configuration state function. According to the laws of quantum mechanics, for systems with only one electron, a level of energy is associated with each electron configuration, and in certain conditions, electrons are able to move from one configuration to another by the emission or absorption of a quantum of energy in the form of photon. So, as the introduction, the electron configuration is the standard notation used to describe the electronic structure of an atom. Under the orbital approximation, we let each electron occupy an orbital which can be solved by a single wave function. In doing so, we obtain these quantum numbers. So the n, m, which are the same as the ones obtained by solving for Bohr's hydrogen atom. Hence, many of the rules that we use to describe the electrons at rest in the hydrogen atom can also be used in systems involving multiple electrons. When assigning electrons to orbitals, we must follow a set of three rules: the AUFBAU principle, the Pauli exclusion principle, and the Hund's rule. So, coming toward the next, rules for electron configuration. So, in order to write an electron configurations, we need to know the rules. There are three rules of electronic configuration followed. The first one rule is AUFBAU principle, the second one is Pauli exclusion principle, and the third one is Hund's rule. Using the orbital filling diagram, as you see in the figure at the right, will help you figure out how to write them. Start with the first orbital. Fill each orbital completely and then go to the next one: 1s, 2s, 2p, 2s, and so on. All of the elements have been accounted for. Coming toward the next, how to fill low energy orbitals. First, the AUFBAU principle states that electrons enter the lowest energy orbitals first. As you see, maximum of 2 electrons per orbital. The lower the principal quantum number and the lower the energy. Within an energy level, s orbitals are the lowest energy, followed by p, d, and f. The f orbitals are the highest energy for the level. So, as AUFBAU principle, the AUFBAU principle from the general AUFBAU building up construction was an important part of Bohr's originally concept of electronic configuration. It may be stated as a maximum of 2 electrons are put into an orbital in the order of increasing orbital energy. The lowest energy orbitals are filled before electrons are placed in high energy orbitals. As we're going from the lower energy, 1s, 2s, 2p, 3s, 3p, 4s, 3p, 4d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5p, 7d, 7p. The approximate order of filling of atomic orbitals following the arrows from 1s to 7p. After the 7p, the order includes orbitals outside the range of the diagram, starting with 8s. This principle works very well for the ground state of the atoms for the first 18 elements, then decreasingly well for the following 100 elements. The modern form of the AUFBAU principles describe an order of orbital energies by giving Madelung's rule or Lechkovsky rules. This rule was first stated by Charles Jeanneret in 1929, rediscovered by Erwin Madelung in 1936, and later given a theoretical justification by V.M. So there are two steps which justified. Orbitals are filled in the order of increasing 1 plus n plus 1. The second step is where two orbitals have the same values of 1 n plus I. They are filled in order of increasing n. This gives the following order for filling the orbitals: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. So 4f, 5d, 6p, 7s, 5p, 6d, 7p, and as 8s, 5g, 6, 7, 7d, 8p, and 9s. In this list, the orbitals in Parentheses are not occupied in the ground state over the heaviest atom known as OGZ is equals to 1 is equals to 18. Z equals to 118. So coming towards the next, this also gives the following order for the filling orbitals: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4s, 5s, 4d, 5s, 6x, 4f, 5d, 6p, 7s, 5d, 6d, 7p. In this list, the orbitals in parentheses are not occupied in the ground state of the heaviest atom known. The above principle can be applied in a modified form to the protons and neutrons in the atomic nucleus as in the shell model of nuclear physics and nuclear chemistry. So no more than 2 electrons in any orbital ever. The next rule is the Pauli exclusion rule. The Pauli exclusion principle states that an atomic orbital may have up to 2 electrons and then it is full. Then spins have to be paired, which usually represents this with an up arrow and a down arrow. Since there is only one s orbital per energy level and 2 electrons fill the orbital. Wolfgang Pauli, yet another German Nobel Prize winner. Quantum number describe an electron position and number 2 electron can have the exact same quantum numbers. Because of that, electrons must have opposite spins from each order in order to share the same orbital. Coming toward the next, and the third rule is Hund's rule. Hund's rule states that when you get to degenerate orbitals, you fill them all halfway first, and then you start pairing up the electrons. What are degenerate orbitals? Degenerate means they have the same energy. So the 3p orbitals on each level are degenerate because they all have the same energy. Similarly, the d and f orbitals are degenerate too. The Hund's rule states that when electrons occupy degenerate orbitals, that is same n and I quantum numbers, they must first occupy the empty orbitals before double occupying them. Furthermore, the most stable configuration results when the spins are parallel, that is all alpha electrons or all beta electrons. Nitrogen, for example, has 3 electrons occupying the 2p orbital. According to Hund's rule, they must first occupy each of the 3 degenerate p orbitals, namely the 2px orbital, 2py orbital, and the 2pz orbital. And with parallel spins, the configuration below is the third electron does not occupy the empty 2pz orbital. Instead, it occupies the half-filled 2px orbitals. This, therefore, is a violation of Hund's rule. So, as the objective D, now that we know the rules, we can try to write some electron configurations. Remember to use your orbital filling guide to determine which orbital comes next. Let's write electron configuration for the first few elements, and let's start with hydrogen. So the electronic configuration of hydrogen, its atomic number is 1. So the configuration is 1s1 as Li lithium, Z is equals to 3, 1s2, 2s1, B is equals to 5, 1s2, 2s2, 2p1 as etc. Note that all the numbers in the electron configuration add up to the atomic number for the element. For example, for neon Z is equals to 10, 2 plus 2, 2 plus 6 is equals to 10. So objectively, one last thing. Look at the previous slide and look at just hydrogen, lithium, sodium and potassium. Notice their electron configuration. Do you see any similarities? Since hydrogen and lithium and sodium and potassium are all in group 1a, they all have a similar ending as 1, as the electronic configuration of hydrogen is Z is equals to 1, 1s1, lithium Z is equals to 3, 1s2, 2s1, sodium Z is equals to 1, 1s2, 2s2, 2p6, 3s1. The last one is potassium, Z is equals to 19, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. This similar configuration causes them to behave the same chemically. It's for the reason they are in the same family or group on the periodic table. Each group will have the same ending configuration, in this case something that ends in 7-1 S1. So the end, this is all from my side. Thank you.